Oh, hey! Oh my god. Hi folks. Hi Procrast. Hi. Oh, Kappa. What's going on, Kappa? Jeez. Wonderful. The whole class is here. Oh, I see people in the Discord. Hello everyone. Awesome. Okay, let's just start, I guess. Why not? Okay, let's see if we can get away with playing some classical music this time. Okay. Hey, what's up? Is that too loud? Okay. Alright, so class. Hey Skugget, how's it going? Hey Sipet. Now you don't have to follow, it's just so that you know we went live. Okay. So, class. Oh no. My brother just doesn't wake up very early, so the bot is broken, I think. Anyway. So the Kummer surface is frozen. Unfortunately. Vixen, I'm sorry. Class, we have a shorter week today. I mean, this week. Remember, there's no class on Wednesday. So it's just a Monday-Friday situation. And my intention is to cover chapters 4 and 5 this week. And that's right. So the homework, which I'm going to post right after class. Wait, did the color change? No, it didn't. Is going to be bigger because I have to cover chapter 2, 3, 4, and 5. But if you think about it, the material is very, very concrete and hands-on. So this should be a fun week. And next week's even more fun. Okay, great. So pay attention to that. And so today, of course, as is customary, as traditional around here, I give a 3-part lecture where I probably only talk about 2 things, and then the third one just goes into the ether. Okay, let's do it. Let's start. The first thing is a definition. How to generate a field with a set of numbers. What that means, just a definition language. Okay. Then I'll get to this thing that I assigned last week. Why the heck is this thing a field? All right. And then we'll discuss other examples, like this one, which I made a mistake last time, and some other ones, whatever. Just play around. Examples. Cool. Okay, so let's begin. Let's begin. Fields are often, for us, fields will often be generated by adjoining a set of numbers. Hey, FemVox fan, how's it going? Okay, so let's imagine the following situation. And we're just working in a very concrete situation. Subfields of C, all right? So we've got C. It's our ambient megafield. And now let's suppose someone gave us a subset of numbers in C. Just a collection of numbers. Okay? Then? Okay. Hi, Crow. How's it going? Okay, then you can create the field generated by this set. denoted Q adjoin X. I'll explain the Q in a second. Is, by definition, the smallest subfield of C containing X. Okay, now what does smallest mean? So let me explain that. This is typical situation in all of like math. You'll find this situation a lot. What does smallest mean? Minimal. Minimal. Okay, so smallest means the following. This is what when you don't have any other tricks up your sleeve. Typically, what smallest means is as follows. If you have two fields, then their intersection is again a subfield. Immediately go prove this. It's the simplest type of proof, yeah? Go prove it. Okay? Simple situation, just like subgroups, etc. Okay. So when you have this kind of a fact, you can talk about the smallest thing containing a thing. All right, so then smallest subfield containing X is by definition, you can take, it's the intersection of all fields that contain X. All right? The K's intersect all the fields that contain X. That is the smallest subfield that contains X. All right? And so you can prove, easy to prove. All right? Easy to prove that. Maybe I should change this to like L's or something. Just to make it not confusing later. Okay? Easy to prove that this field, if M is any field containing the set X, then this subfield generated by X must be contained in M. And so in this sense, it's also the smallest under containment. Why do you need to have an overarching set? Isn't Zorn lemma enough to deal with the abstract case? Is there another canonical notation if the overarching field is, say, a set of rational fractions or some weirder field? No. We can I'll generalize this immediately, this definition. But you do need an ambient field because I'm starting with a subset of that stuff. Right? Look. I'm starting with a subset of this ambient one. So I can't even parse the sentence without an ambient something to start choosing new numbers from. Okay? Good question. Hey, N Burrows, how's it going? Shout out. Go check out N Burrows for chemistry. And karaoke. All right, good. Okay? So that's what we mean. It's the smallest subfield containing X. Smallest in set theoretic sense. Great. All right, Crow. Yeah, very good, Crow. Yeah. We'll discuss it as a community. Right. Okay, so slight generalization for kappa. Suppose we begin with a field extension. And for concreteness, just think about these as subfields of the grand field C, if you want. Okay? Suppose you have a field extension. And suppose that Y is a subset of numbers in the bigger field. Then again, you can define the field, the intermediate field generated by Y. It's called K, the small field, adjoin Y. And we let this equal the smallest subfield of L containing K, which also contains Y. So it's the smallest subfield. Both K and Y. Okay. Wait, smash time. Wait, smash time. You located Bob? Oh no. Oh no. Oh my god. Okay, so notice that K of Y is what we call an intermediate field. Notice. KY is an intermediate subfield. It's sandwiched between the big field and the small field. And Galois theory is all about this situation, really. You have a small field contained in a big field, and we in a sense just want to study the structure of all intermediate fields. And one way of generating intermediate fields is just by like doing this generate with a set operation. Okay, in fact, that's the only way to do it if you really meditate on it. Okay, let's do some examples really fast. Okay, yeah. Let's do a couple of types of examples. Here's one that don't think about it too much, but here's one. What is Q adjoin the empty set? Don't think about this. Don't think about it too much. Empty set cases. It's actually Q. Okay? Because if you unravel the definition, Q adjoin X is the intersection of all fields containing X as a subset. But every single field contains the empty set. Okay, every field contains the empty set, and not only that, every subfield must contain Q. So in this sense, Q is the bottom of the tree of all fields inside of C. All right? Why is the last thing true? Why? Because every field contains the element 1. And if it contains 1, it contains 2. And if it contains 2, it contains 3. 2 plus 1. And then 4. But then it contains all the minuses. It contains Z. But then it contains all the inverses of things. If you give, you remember those storybooks? If you give a mouse a cookie, it's gonna want milk. And then if you give it milk, it's gonna want a napkin or something. Or if you give a moose a muffin, it's gonna want this, and then etc. All right? Good. Okay. Awesome. One small favor. Yes. Music too loud? RDL? The Moose theorem, yeah. Oh, it's a joke. Good. I'm cultured. I know these things. I know RuneScape and all that. Okay, ready? Great. Let's do some better type of general example, all right? Okay. Another type of example. It's when you adjoin a single element. All right? So if you have a field extension, and if you take just a single element, then we write simply this, K adjoin Y, for the smallest intermediate field that contains Y, right? These kinds of fields are called primitive or simple extensions. I prefer primitive. Book uses simple. And you'll understand why I prefer primitive later. These kinds of extensions are called, let's call it both, simple/primitive. Just adjoin a single number. Why are we talking about this? Go read the 3 sentences of Galois theory and then puzzle over that. Okay, next. Let's talk about one particular primitive extension that came up in homework last time. It's a primitive extension of Q. All right. It was this thing. It was called Q adjoin alpha, where alpha was the real cube root of 2, say. Okay? Now, the claim was that Q adjoin alpha is literally this set. I'm going to write it like this. Okay? That's a claim. Because what is the content of this statement? The content of this statement is that the right-hand side is a field. And then, if the right-hand side is a field, it must be equal to the field generated by alpha. The extension of Q generated by alpha. Okay, so that's the two-part content. All right, so one, the right-hand side is a field. Now it's easy to see that it's closed under addition, subtraction, multiplication too, because the alpha cubed comes back and cycles back to a 2, which kind of... Okay? So it's clear that it's a sub-ring. But what's not clear is that inverses are in there. That's not clear. Inverses are in there. So the issue was inverses. And I know Femvox fan was asking about this and so on. Okay? So you can do really ad hoc things and show that these kinds of numbers have an inverse again of this form. You can do ad hoc things. But I want to discuss a more general way to go about this thing. So let's talk about the inverse problem. Why? And let's do it in a way that generalizes. Okay, so what the reason why inverses are there, the true answer is going to make you appreciate the beautiful structure of a polynomial ring in one variable, namely that it's a principal ideal domain. That's the real sort of heart of this of the explanation. Okay, so let's talk about this. So step 1. Write down the following ring. And in it, write down the following element. Okay? That's step 1. I'm giving it steps so you can write it in your note cards. Step 2. Observe, crucially observe that t cubed minus 2 is irreducible in over q. So it's an irreducible element in this principal ideal domain. U adjoin t. All right? Polynomial ring. Why? Use Eisenstein, for example. Hammer. I mean, it's not a hammer. We just, for example, or it just, if a cubic is irreducible, if and only if it has a root in that field. Right? Linear times quadratic. And it doesn't. Cube root of 2 is irrational. All right, good. So this is Eisenstein. Like, okay, done. So we've got ourselves an irreducible polynomial. Okay, so now, step 3. Imagine taking an arbitrary quadratic polynomial and putting it on the page. And make sure it's not the 0 polynomial. Thank you, Smash Time, for giving nice facts so that the students can learn more if they want to go deeper into this subject. Thank you. How would this change for general alpha? Like pi or something not in R? It is a good question. This polynomial, f of t, you wouldn't be able to write down a non-zero one. So you wouldn't be able to do step number 1 for pi. But yeah, we'll deal with pi on Friday. Those kinds of situations. Procrastinate. Okay, good. All right. So look, if you have an arbitrary quadratic, right? If you have an arbitrary quadratic, then not 0. Then this polynomial, we can call it g. This polynomial has to be relatively prime to f. Must be relatively prime. Cannot share any irreducible factors. Because g of t has smaller degree. And the only way f and anything can share a factor is if the factor is f. F is irreducible. It's like a prime number. Okay? All right. So f and g are relatively prime. Okay? But that means that the highest common factor, a highest common factor, of f and g is 1. And we say this ideal theoretically as, okay, let me say it sentence-wise. But in terms of ideals, this ideal, all linear combinations of f and g, ring linear, polynomial linear combinations of f and g, that's the whole ring. It's the principal ideal generated by the highest common factor. Okay? Which, by the way, is the whole ring. Which is to say, there exists two polynomials a and b, so that af plus bg equals 1. Okay, look, this is a powerful trick. All right. And now, all I'm going to do is sort of write out the variables. Maybe I shouldn't call it a and b. I should call it c and... no. Capital A and capital B. And now what I'm going to do is plug in alpha. T equals alpha into this thing. And notice that when you plug in t equals alpha, this thing goes away. That's why I chose this f to begin with. And this f has a name. It's called the minimal polynomial for alpha. Of the element alpha. Okay? This thing goes away, and what are you left with? You get this times this equals 1. But what is g of alpha if you really pay attention? Oh, hi. Hi. If you really pay attention, g of alpha is an arbitrary element in this ring, in this field, in this ring. Non-zero, non-zero. Okay, so the inverse is b of alpha. And please notice B was a polynomial. It didn't have negative powers or anything. B was itself a polynomial. This was itself a combination of powers of alpha. And yes, it could have higher powers of alpha, but higher powers of alpha cycle back around. So B of alpha is the inverse of G of alpha. The inverse exists. Why? Because of the structure, the simple structure of a principal ideal domain, that Q of T is a principal ideal domain. And so we're using the fact that Fg equals the ideal generated by the highest common factor. Only that little bit of structure is what's letting us deduce that if you start with the irreducible polynomial satisfied by the number, then this argument's going to show you, this argument's going to crack every single nut, basically, whenever you adjoin a single element. Okay? Now, it's an art form to try to find this particular polynomial, but we'll deal with that later. All right? So the fact that it's a field emerges just from the structure of irreducible elements and A, B, this kind of identity, this kind of trick, which you've seen before in the polynomial ring. All right? It's wonderful. Yes, Femvox, yes. Ideal generated by. All right? Okay? Now, the issue here is, this tells you this is a field. This kind of argument's going to work forever, as long as your f here is an irreducible polynomial. So the problem, though, is that it would be nice if we knew how to compute the inverse of an element. But actually, in this discussion surrounding it, there's a thing called the Euclidean algorithm, which will actually help you find that capital A and the capital B that make this identity true. So one question you can ask is how to find A and B. And for that, I want you to go read in chapter 2 or 3. Now go read and appreciate the Euclidean algorithm, which tells you how to get down to an expression, capital A and a capital B, all right? The key is Euclidean algorithm. And it'll show you how to do it algorithmically for every single example in principle. Okay? Yo, not prof, how's it going? We just using the fanciness of the principal ideal domain structure of Q adjoin T, or field adjoin T, figured out why when you adjoin a cube root of 2 and then also tack on its square, why that collection of numbers forms a field, right? Awesome. That's great. Okay, so class, if you have no... Is the Euclidean algorithm supposed to be obvious? I felt it was quite non-obvious. It's obvious. Yes, it's obvious. It's obvious because there's a notion of degree. The notion of degree means that at each stage of the algorithm, the remainder is getting smaller in degree, so it must stop. So the fact that you have an algorithm that halts is obvious. Yeah? And that's all you need. You just need that procedure, and then you reverse read it to get this expression. Oh, right. That it returns the HCF is not obvious. That's right. That's true. That's true. Okay? That's true. It's actually it is kind of obvious. No, it's not obvious, but yeah, it requires a proof. Yeah. If the point is that the last remainder divides both A and B, both F and G, because you can reverse, go back, reverse. And that's the tricky part. The other direction is that anything dividing F and G has to divide the last thing is obvious. More clear. Okay, so the Euclidean algorithm is appreciated most in our class so far. In the question, what's the exact expression of the inverse? And you can actually execute it with completely in this example, and I encourage you to do so. But the real thing to appreciate is simply the fact that the Q adjoin T is a principal ideal domain, which tells you that there must be an expression of this form without telling you how to find it. Great. Okay. So next. Hey, Mr. Rogam and Wavjug and Eminem and not Prof. How's it going? Yeah, they'll benefit from Galois theory? Yeah, exactly. Okay, great. So now, we just settled this example, and as you can see, it's gonna settle every primitive simple extension. Y is the thing where I just take the number, it's square, it's cube, Q, Y, and then stop when it cycles back, if it ever cycles back in some way. Why does that set of numbers form a field? It will go through the same exact argument. Let's do some other kinds of examples. Do some other types of examples. That second chunk was for appreciation of the PID structure in polynomial ring. Let's look at a third thing. That's very high, fancy. You know, I see people making fun of me in other people's chats, like, oh, he likes fancy things like sheaves or something. Yeah, people make fun of me. Yeah, they're idiots. They don't realize this abstract algebra gives you the real reason why things are true, not your like ad hoc, simple, clever manipulations. All right? Yeah, good. All right, let's keep going. Let's go back. Let's go down to earth. Yeah, let's do this. Let's adjoin two numbers to Q. Let's stick to Q. So here the set is two numbers, square root of 2 and square root of 3. Okay? Square root of 2, square root of 3. All right. I want you to observe that this field, this is a field. This is a field. This field is not just naively, as we saw last time, the following. This is not okay? You have to add more. We saw that the square root of 6 is not contained in this set, but it needs to be contained in the field. Because if it's a field, it's closed under multiplication. So it has to be, so it has to at least be okay? Okay? It has to at least be this. All right? And if we show that this is a field, if you know that this is a field, then square both sides, collect, and then you get the irrationality of square root of 2 or something. Square both sides and collect, and it amounts to irrationality of the square root of 2. You end up with a bad thing. Okay? So this polynomial is an irreducible polynomial in that polynomial ring. Boom. Same exact argument. Every polynomial ring over a field with one variable polynomial ring over any field conceivable is a principal ideal domain. So that's the power of the abstract algebra. All right, so then all the other steps just flow out. Okay? Great. So that's why this set is a field again. This set's a field again, but this set is equal to this set. All right? Okay? So is it like buzzing again? Oh no. Electrified? Okay. Yo, Root Guy, what's going on? Root Guy is definitely a family member, probably an auntie. Hi auntie, how's it going? Okay. So I just wanted to highlight the power of the structure of a polynomial ring to deduce that something's a field without actually doing it by hand. All right, that's great. So now I'm going to say something very confusing if you've never seen this before. This looks like it's not a simple or primitive extension. Let's use our thing. Look, the set X had 2 elements. However, it is primitive. So I know the class is done, but just last little note. Foreshadowing. Doesn't look primitive? Doesn't look like a simple extension? But it is. In fact, this field is the same as the following field. Q adjoin one number. Let's call this beta. These are the same fields. Notice there's an obvious inclusion one way. Obviously, that's because this element is already in this set, right? We know what the field looks like now. It's just this. Okay, obviously, I took an element in there and I generated by that. So we already have this inclusion. Now you have to get the reverse inclusion, all you got to show is that the square root of 2 and the square root of 3 are contained in Q adjoin B, beta. Okay? Okay, so for this, you're gonna need to do some clever math. You need some clever. Because all you've got is this beta. But if you square beta, okay, if it's clever, I'm not gonna be able to do it. Watch me fail. Ready? Square beta. So, beta squared minus 5 all divided by 2, which is of course in Q adjoin beta. Is just 6. Square root of 6. Square root of 6 is in this field. Now, if square root of 6 is in the field, I can multiply that by beta. Hopefully this is going to get somewhere. Is this going to get somewhere? Is this going to get somewhere? This is? Okay, hold on. What's square root of 12? Thank you, Smash Time. Okay, this is gonna get somewhere. Okay, square. Wait. I'm dyslexic or whatever. 2 cubed. Wait. Oh my god. Just barely. Okay, just barely. Okay. But then you subtract. This is beta. So like, I'm only doing field operations with beta and rational numbers. So you earn square root of 2, and if you did it some other way, you'd earn square root of 3, or obviously, you earn square root of 3 right away. And then beta minus square root of 2, so this is in... So, lesson. Just because something looked like it required 2 or 3 generators, or 10, doesn't mean it secretly might not require fewer. Now there's an art form for finding this type of simpler generator, and you might have questions like, is every extension secretly simple? For the answer, stay tuned. Okay, good. So now let's look at the degenerate chat. Okay, everyone can go home now. Okay, I can't believe I got through that example just live on live national TV. Yeah, cliffhangers. Yeah. That's right, Smash Time. Any finite separable extension. But we're in the complex numbers right now, so the separable part will be kind of confusing. Okay. Absolutely. Okay. That's right, Smash Time. You remember finite separable extensions. Boomer Surface Gang. That's right, Root Guy. Thank you, Auntie. Thanks for the support. Okay, where did the music go? Okay. Well, this was really fun. No class on Wednesday. And that's right, Kappa. That whatever you said, that's right. Sure. Whatever you said, yes. Okay? Yeah, no class Wednesday. Class resumes Friday with concepts where the point of Friday is to start talking about different kinds of elements from the generating extension point of view. Algebraic elements versus transcendental elements. That's the content of Friday. Okay? We'll talk about that. And then next week is ruler and compass which is always fun to see if you haven't seen it before. Yeah, you too, Femvox. I guess maybe not everyone is. Not everyone's having a break on Wednesday, but see ya, not prof. Thanks for hanging out. Yeah, no class, bro, on Wednesday. No, it's not. It's not because yeah, it's not. Thank you, Auntie. Root Guy is an auntie. Auntie supports the stream. It's amazing. Oh, sorry, Femvox. The thing is, we eliminated spring break this semester, but to keep students, you know, to punctuate the semester, we've sort of spread out days for just relaxing, and the first one is Wednesday. Oh, nice, Professor GCD. Hey, Professor GCD will know how to use the Euclidean algorithm. It seems. It's a world expert at Euclidean algorithm. Awesome. Is NLP? Yes, I know what that is. You want me to talk about NLP? Hold on, I'm just checking my email. So NLP, in my opinion, NLP is neuro-linguistic programming. It's a pseudoscientific approach to communication, personal development, and psychotherapy created by Richard Bandler and John Grinder, in my opinion. In the 70s, NLP's creators claim there's a connection between, on the one hand, neurological processes, Crow, and language, linguistics, and behavioral patterns, third hand, learned through experience. So that's what NLP is. Okay?
Yes, science. Yeah.
Good. I can lecture about basically anything. I just discovered this a couple days ago. Yeah, any subject. I could just go and give a lecture on it. I didn't know I had this power before Saturday. Yeah. Oh, really? The professor's missing? That's scary, dude. That's scary. Oof. The class is starting in 2 hours and no one knows anything. No emails, no posting. Wait, that sounds like... Are you in my class? You might be one of my students, bro. Anyway. Okay. Hey everyone, all three of you. What happens at the end of class? Not all at once now. Please. We go home. But what makes you happy? What? You don't want to go home sad. What boosts your happiness? Kappa, deliver pizza. It's credits time. It's time for the credits. This is what everyone's waiting for. To be called out by name. All right. Okay. Pineapple and onion. Okay, well, we've got Vixen. Vixen's here. Friend of the stream. We've got Crow. We've got all my students who I saw you. I saw you in Discord. I see you. I saw RDL in chat. Maybe another. I don't know. But all my students. Watch out for my homework drop right after I go off air. I'll choose some problems from 2, 3, 4, and 5 chapters. Sounds like a lot, but it's not. It's easy stuff right now. All right. RDL. Another. Itis. So on and so forth. Okay. Crow. Welcome. Kappa. Hey. Hey folks, did you all know? Did you all know that Kappa streams Diablo? Go follow Kappa. Go follow Kappa right now. He has 95 followers. Get it to 100. Get it to 100. Come on. Our beloved Kappa has been hiding this from us this whole time. And it's really pleasant. I just went there earlier today while learning all of this material. I was listening to Kappa. Awesome. Great. Really fun. Okay. Yo, Rambo Infinite shows up with a comment. Hey, Rambo Infinite, how's it going? Okney Blap, hey! How are you? Hope you're having a good day. Hope everyone has a good day. Moving forward here. Professor GCD, king of the Euclidean algorithm. Or queen. World class. Let's see. Femvox, of course. Femvox. This is Femvox's favorite part of the stream. I got you. Don't worry. And who are our mods here? Was Arbitrary here? No. But you know who was here? One of the most reliable mods in the universe. Smash Time. An ancient friend of mine. Man, I just keep remembering those days. Nostalgia. Smash Time. So many memories. Alright. Did I get everyone? Did everyone... How could I forget Root Guy Auntie? Auntie Root Guy? Hi, Auntie. I'm just assuming. I mean, it's gotta be. Why else would you subscribe for 2 months, Auntie? Let's see here. Not Prof showed up. Not Prof. Let's not forget that. Let's not forget. Yo, Pandemic was here. Pandemic. Did I get everyone? I think I got everyone, didn't I? That's right. Oh, green check mark. You know what I need to start doing? I need to start checking everybody to see if they stream. And then... embarrassment all around. Procrastedigitation here early. I did, Professor GCD. I did. I got Professor GCD. Alright, did I get everyone? Rodelf? How's it going, Rodelf? Alright. I got my did I miss any requests with channel points? No, I'm thankful for that. Present. Nice. Okay. Recorder? I shouldn't have said anything. Since we're playing classical music. You want me to juggle too? Okay, we can juggle. Juggle, and then I gotta go. Juggle, then we quit. Got it? That order of operations. Here we go. Boom, 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 boom. I'm gonna do 5. I'm gonna do 5. Here. Let's see if I can do 20 throws. Okay, I think I can do it. I think I can do it. Count it. It was 20. It was right there. 21, 22. Oh my god, I can't believe it. And 20 is the official benchmark for saying that you can juggle 5 balls. So it's official. If you look at the World Juggling Organization's criteria, it's official. Yo, Vixen. All my students, smash time. Femvox, Crow. Sorry the color changing thing didn't work for my Kumar surface. We'll try to be better about that. And I think we have one more emote showing up. Probably relevant when I make mistakes, which will happen a lot. Such a high prime integer. 57. I'm not that bad at math, Kappa. Nice try. Alright. All these people, wonderful people. Makes it fun to teach. Yeah, pandemic 4 is uninteresting. No, 4, okay, if you want to do cool stuff with 4, it's kind of really hard for me. Because you gotta do some kind of irregular something. But yeah, that's why I skipped 4. Look at the level of discourse in our math chat. We've got people adding 5 and 7 and saying it's 6 plus 6. We're the lowest common denominator. All right. Yo. Femvox thinks Crow should be modded. We're gonna have to vote on that. Let's just vote real fast. Hold on. Get your voting things on. The 1 minute poll. Ready? 1 minute poll. 1 minute. Ready? Start the poll. Vote, vote, vote. Look on the top of the screen. There's only 3 people voting? 4. Oh, it's tied. It is tied. 3-3. Oh my god, this is exciting. 30 seconds. 30 seconds. Wait. Someone tie it. Make it tied, someone. There's only 7. Yes. Okay, now stop the count. Stop, no. Tie it. Stop the count. Stop. Oh, yes. This is history. This is history. Oh my god. This was really fun. It's the first time I ever had fun on stream. Oh my god, Crow. This was just... Couldn't have asked for a better, more dramatic finish. Schmo Knight, here's the sticker. You go like this. This is a sticker. Schmo Knight. Hey, Schmo Knight, you're here. I see you. Hope you're having a good day. Okay. You're gonna run again, bro? Okay. They won't. No one comes back here. There's like 3 people that keep coming back. The rest are just like bots. It'll be a new batch of bots, bro. Maybe it'll work out better next time. Okay, let's go. Let's get out of here. Let's go, you wanna learn some chess? I don't know anything about chess, but I like watching it. Okay? You wanna go watch some chess? It's intellectual, right? It's like high class. I mean, we have our like classical music here. You know, it's good. Hey, Rambo Infinite, have a good day to you. Okay, you know, it's like smart thing, you know, you're supposed to do. Oh, okay. All right, see you, Femvox. All right, I'm rating now.
Right up. Damn. Yeah. I mean, isn't